everybody, it's Ms. Phoebus, and I'm back with another lesson, lesson 52. We're going to look at some patterns and sequences, as well as some arithmetic sequences. So there are going to be some problems in the notes that we are going to skip. If you want to go over those problems with me in a Google Meet, that would be a perfect time to do it, especially if you're having trouble with something. Make sure that you are watching the videos on the days they're posted. If you are waiting and you're getting behind, okay? So make sure you're watching them on the day that they are posted. If you're doing that, great. If you're listening to this and it's the day after, just know that you need to get caught back up because you're missing a lesson before test day. All right, so I do want to talk to you really quickly. I did get some more information about testing. So if we are coming back in person after Thanksgiving, or after November 30th. If we're 100% in person, and I know that means that some of you are still virtual, but most everybody is here. We are going to be taking our end of course test December 7th, 8th, and 9th like we would normally do. That means that all of the statistic stuff will get pushed to the end later after the end of course test, and that's just going to be how it's going to be. If we are going to stay 100% virtual, what that means is that you will come to the building, but all Algebra 1 students will come on December 11th. That is a Friday, so that's at the end of that week where 7, 8, 9 are. It's just Algebra 1 students. It's basically just my students. So if you're in my class, you're testing. And then if you are virtual, they will have a separate place for you to test away from everybody else. But that is the day that I have the Unit 8 test scheduled, which it'll be really easy. We'll have talked about all of our stat stuff. We will just bump that test to the following week. I might not do a Monday test. I might give you an extra day to make sure you're good on everything. And then test on Tuesday. So I'll play around with that a little bit. But that's what they've put out officially. So what we're waiting on is to hear before Thanksgiving break. It's the 23rd. There's a board meeting, and we're going to hear what they decide, if we're going to go back full after the 30th, or if we are going to be remaining virtual for pretty much, I guess, the rest of the semester. I don't know. But just to give you a heads up, that's what end of course is looking like. So I've got a lot of stuff left to cram in, and I'm going to do the best that I can, but and I don't want to overwhelm you. Just know that I am trying to prepare you for a test that is going to count. And I want to make sure that you are adequately prepared. So if you are slacking and not doing what you're supposed to do, you're going to feel overwhelmed. If you've been pacing yourself along with me, then hopefully it won't be too bad. And I'm going to work and try to cut this video down to where, so if you're like, hey, we're on something totally different, a couple pages later, that's what happened, okay? Is that we've just kind of moved on and we're going to talk about something different. So I'm going to introduce patterns and sequences to you, as well as arithmetic sequences. Arithmetic, not arithmetic. All right, some words that you know or already think you may know. Arithmetic sequence, which is a sequence of numbers that has a difference between the consecutive terms that is constant. So it means I'm adding or subtracting the same thing over and over and over again. It's a constant difference. So 5, 7, 9, 11, 13, 15. The common difference is 2. I'm adding 2 each time, every single time. Didn't add anything else, didn't subtract something. It's always 2. So that's how you know it's arithmetic. A geometric sequence is a sequence of numbers where each term after the first is found by multiplying or dividing. Now with multiplying, we'll talk about, multiplying by a certain number. When we talk about dividing, we're actually going to involve our fractions. So in this case, we've got 2, 4, 8, 16, 32. We're multiplying everybody by 2 each time. in our state standards, we need to be able to construct linear and exponential functions. So we're going to focus on the linear piece today, but know that geometric is going to go along with our exponential functions, including arithmetic and geometric sequences, given a graph, a table, a description of a relationship, or input-output pairs. So we're on page 256. We are actually going to try to go through 3 of my book lessons. And like I said, I'm maybe cutting stuff out to try to save us on some time. So just kind of follow along and enjoy the ride. Enjoy the ride, ladies and gentlemen. All right, here we go.
All right, so our types of sequences that we have, of course, we've already talked about arithmetic. It's a pattern of numbers that increases or decreases by adding or subtracting the same number every time. Now, that same number, I've italicized common difference. That word you need to know. Common difference indicates that you know how the sequence is changing. You're looking at that number that keeps coming up. If that number is not the same number, it's not a common difference, it's just a difference. Of course, as I'm going through the notes, I'm just going to keep going. If you need to pause it so you can write, go for it. So here we have some examples. So 17, 22, 27, 32. So we're adding the same number each time. And so we're adding 5. That is our common difference. Our common difference is going to be 5. Here I've got -3, -11, -19, -27. I'm subtracting the same number each time. So because I'm subtracting the same number, my common difference will be negative. And so my common difference here would be -8 because I'm subtracting 8. Geometric is a pattern of numbers that increases or decreases by multiplying or dividing the same number every time. So that is called a common ratio. So there's a difference in common ratio and common difference. And so you need to make sure you understand the difference between those two phrases. For geometric, we have 2, 22, 242, 2,662. And so our common ratio is that we're multiplying by the same number and we end up multiplying by 11. So our common ratio is 11. And then 48, -16, 5, and really that's a third, and -1.7 repeating, which I don't remember what the fraction is, but it looks like we are dividing by, well, sometimes it's hard to tell what we're dividing by. So one of the ways that we can figure out what we're dividing by is we can take -16 and we can divide that by 48. So you're going to see me do that a little bit. Take the second number and divide it by the first number. So I'm going to grab my calculator. I don't know if you'll be able to see it. I'm going to type it in here. -16 divided by 48. And then I'm going to change it to a fraction, which it is a fraction, -1/3. So I'm dividing by -3, or I'm multiplying by -1/3. And you're going to hear me use that quite often as far as we don't state division, we state multiplying by a fraction. So that's your geometric sequences. Fibonacci sequences are a pattern of numbers that uses the numbers in the pattern to create the pattern. And so we, of course, have our Fibonacci does start with 0. So 0, 1, and then 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. That's the original Fibonacci sequence. But I can create my own Fibonacci sequence. I can pick two numbers, any two numbers. In this case, I picked 5 and 50. And to create the next number, I just add them together. So 5 plus 50 is 55. And then 50 plus 55 is 105. And then 55 plus 105 is 160. So I've created my own Fibonacci sequence. It's not the true Fibonacci, but it's made by adding two previous numbers together. You could also do that with subtraction if you wanted to. So it's not arithmetic, it's not geometric, it's something else. there may be a pattern, but not anything that you've seen before. So like our triangular numbers and our square numbers, those would be considered others. So a set of numbers that is not one of the patterns above, this could refer to a pattern that is both arithmetic and geometric. So it's like, well, I'm adding the same number each time and multiplying by the same number. That you can't slot them into both categories. So you would just say other. So some examples are 2, 5, 11, 23, and 47. And looks like here I added 3, here I added 6, here I added, is that 12? Here I added 24, so it looks like I'm adding multiples of 6, which that doesn't work. And then here are square numbers. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, so on. So those would be considered other. So when I'm looking at a sequence, which we're going to do in a minute, and I'm trying to figure out is it arithmetic, geometric, Fibonacci, or other, I usually start with arithmetic. Could I add the same number each time? No, that doesn't work. Let's try geometric. Let's try Fibonacci. No, then it's other. And then we may be able to figure out what that pattern is and be able to extend it. So here we have, I think it's 5 rows of numbers, practice problems. And if you want to pause this at any point in time, you can to try to practice on your own, which is a good idea. But basically what we're going to do is we're going to classify the sequence, and then we're going to find the next 3 terms. So in row 1, I'm going to look at how am I changing to get to the next number. It looks like I'm adding 2 and then 3 and then 4 and then 5, which that means that's our triangular numbers. Our triangular numbers are going to be adding the next number in the sequence. So the next numbers would be 21 by adding 6, and then 28 by adding 7, and then 36 by adding 8. So that would be considered other. That is our triangular numbers. All right, the next ones, we got to figure out what the pattern is. I always start with arithmetic, just that's what I do. And looks like it is arithmetic. It looks like I'm adding 3 each time. So if I add 3 to 46, I get 49. 49 plus 3 is 52. 52 plus 3 is 55. So that is arithmetic. All right, the next sequence looks like I'm subtracting 5, adding 16, subtracting 48. That's crazy. If I look at geometric, looks like I'm multiplying the first round by -4 and then by -3. So these two, if I continued on with multiplying by -3, that would work out. But because this isn't the same number, it has to be the same number all the way throughout, we cannot say that this is geometric. We're also not doing anything with these numbers to create some sort of Fibonacci sequence. So this is other. I cannot complete the pattern. That is something that can happen. It's one of those kind of all ball things. But the thing is that you have to check all the numbers. You can't just check like the first 2 and not check every single number. That pattern has to apply all the way throughout. The pattern doesn't apply all the way throughout, then there's no pattern that you can actually create with that. Row 2 looks like I'm adding 5, adding 6. Oh, can't complete the pattern. Now, if I knew that I was adding 5, adding 6, and adding 6 next, then I could maybe complete the pattern and do maybe adding 7. Right now, there's not a whole lot of information on that. So I don't feel like I can complete the pattern. I might be able to come up with something that, works, but it is one of those others. All right, the next one, 2, 4, 8, 16. Looks like we are multiplying by 2 each time. If I was going to say adding, here I would be adding 2, here I'd be adding 4, here I'd be adding 8. Yes, there's a pattern in that, but I'm not adding the same number each time. But multiplying by 2 does work. So 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. And so that is a geometric pattern. All right, for the last one in this row, looks like we are, if I'm going to add 0.15. Ooh, plus 0.15, plus 0.15. So keep adding 0.15. And we will extend that pattern out to 0.7, 0.85, and 1. And that would be arithmetic. I'm so thankful that the screen's there, or the problems are there. Row 5 looks like it's going to be Fibonacci. And so we can extend that pattern out. And you can kind of see if you get rid of the decimals and the zeros, it's 1, 2, 3, 5, 8, 13, 21. So it's Fibonacci. On the next one, looks like we're decreasing each time. And we're going to, decreasing means that it's either going to be geometric or arithmetic, possibly, but talking about subtraction or division. Because I'm rotating between these positive and negative numbers, it's probably going to be division by a negative number. And if I divide each one by -2, 8 divided by -2 is -4, -4 divided by -2 is 2, 2 divided by -2 is -1, -1 divided by 2, -2 is 1/2, 1/2 divided by -2 is -1/4, and -1/4 divided by 2 is 1/8. All right, and the last one, I think in Fibonacci, because -2 and -3, if I add them together, I get -5, -3 plus -5 is -8. So we do have a Fibonacci sequence going on. Equation. So it's an equation, it's a rule, it's a formula, all of those things kind of go together, but it is something that models a particular sequence. You input the position value in for the variable, and the equation will output what term is in that position in the sequence. So here we have a sequence 0, 3, 6, 9, 12. And so with this sequence, we can see that we are adding 3 each time. So we're going to write that in our rule box, that we are adding 3 each time, and that makes this arithmetic. So when we talk about position number, we are talking about there are numbers that are first, and then there are numbers that are second, and third, and fourth, and fifth, and so on. So when we talk about term number, we're talking about what position this value is in. So we have the first, second, third, fourth, and fifth numbers, and so I have that filled in for term number, or position number would also work. And then the value, what numbers are actually there, are 0, 3, 6, 9, 12. So this is saying that 0 is first, 3 is second, 6 is third, 9 is fourth, 12 is fifth. And what we're going to do is we're going to graph these. So I am going to have 1, 0, 2, 3, 3, 6, 4, 9, and 5, 12 doesn't fit, but I've got a good, at least a good 4 of them on here. Now, we are not going to connect these. This is discrete, so we do not connect the dots because we're not using all the numbers between 0 and 3 and the numbers between 3 and 6. We're just using those individual values, okay? But if you notice, this is arithmetic and we're adding 3 each time. If I was to connect these with a straight line, that would be linear, and the slope would be up 3, right 1, up 3, right 1, up 3, right 1. So it would have a slope of positive 3. So this is an arithmetic function, and all arithmetic functions can be represented by linear functions. And so that's going to get into what kind of equation we're going to write later. Let's look at example 2. We've got 4, 2, 0, -2, -4. So the rule is, the pattern that we can see as we go to, to the next number is that we are subtracting 2. Again, adding and subtracting the same number each time, that means it's arithmetic. All right, so we have the first number, the second number, the third number, the fourth number, the fifth number, and which number's first? 4. And then 2 is second, 0 is third, -2 is fourth, and -4 is fifth. And if we graph those, we again will be able to see that this is very linear and that we are subtracting 2 each time. That creates a slope of down to right 1, down to right 1. So it's still discrete. It's modeled by a linear function. And because we're subtracting 2 each time, its slope is -2. Isn't that cool? So arithmetic sequences have a constant difference. A constant difference. And sometimes that's called a common difference. Common difference is represented by the little lowercase letter d. Okay? And that's what you're adding or subtracting to get to the next number. So if you're adding to get to the next number, this will be a positive value. If you're subtracting, it'll be a negative value. And the common difference has to be the same all the way throughout. Now, if you're having trouble figuring out what the common difference is, you can always take the second number and subtract the first number. So 3 minus -1 would be 4. Sometimes it's a little bit difficult at the beginning. If you want to skip down to a little bit further, you can take the number on the right and subtract the number on the left. So 11 minus 7 is also 4. So it's a little way to figure it out, and that's why it's called common difference, because they're all common, right? They're all happening, it has to happen all the way throughout, but the difference part comes from the second number subtracting the number in front of it. All right, arithmetic sequences are modeled by linear functions, and that's always. And then the next part, this explicit rule, I have a formula for you. Now this formula I expect you to have handy when you take a quiz or a test, because this is like how you're going to write your explicit rules. So definitely make sure you write explicit rule, arithmetic sequence, and here it is. Now, some of these pieces look a little bit weird. So we have this piece and this piece. Definitely, we're going to have to talk about them. This is your common difference, and this is the position. And I'm going to have some different things pop up, but these guys are new. And the reason why people struggle with exponential, not exponential, explicit rules, and then later on we'll talk about recursive rules, is the notation. So this is A, and then the little n, you read it sub n. So this is A sub n, and it takes the same place as y, like y equals. And what this is this is the nth term. Nth is a really good, if you play Scrabble, nth is a really good word if you don't have any vowels. It's in the dictionary, I promise. It's the nth term. And that n takes the place of the position. So if I want the 22nd term, this would be A, and I would write a little 22. If I want the 105th term, this would be A, and I put a little 105 down here. So that represents a specific term. When you don't know what term it's going to be, it's just going to be with it an n down here. So that's A sub n equals A sub 1. Now A sub 1, there's a number there, there's not an n. So that would mean that this is the first term. So whatever the first number is, that's going to go in that spot. All right, we're going to skip to n. N is the position number. It's usually when we are dealing with writing the rule, writing the equation, this is going to be a variable, as well as A sub n is going to be a variable. So it's almost like it takes the place of x, and A sub n takes the place of y. But most of the time you're going to see it just be a variable. And then the lowercase letter d right there is going to be your common difference. So really, to write these, you just need to know the first term and the common difference to write the explicit rule for an arithmetic sequence. So here I have the formula up on top. And what we're going to do is we're going to write the explicit rule. Now for the first two, 5 and 6, we actually have to figure out what the first term is and what the common difference is. For 7, 8, and 9, they already give it to us kind of spelled out. So what we're going to do is for 5 and 6, we're going to figure out the first number in the sequence, which that's going to be A sub 1. And then we're going to figure out the common difference, what we're adding or subtracting each time. That's going to be the little lowercase letter d. And pretty much we're just going to pop them into the right spots, and then we'll be done. So for number 5, our first number is 11 because 11 is written first. So for number 6, the very first number is 85. So a sub 1 is 85. All right, let's go back to number 5. What are we doing each time to get to the next number? Looks like we're going up, so that would mean that we're adding. We are adding 9, because if I take 20 and subtract away 11, 20 minus 11 is 9, or 29 minus 20 is 9. All right, for number 6, let's see our common difference. We're going down, so that means it's going to be a negative number. Looks like we're subtracting 8, so the common difference would be negative 8. All right, so the rest of this, once you have those values, now I have everything that 7, 8, and 9 have, right? I have a sub 1, I have d. So what I want to do is oh, look at there. There's all my formulas. Okay, and what we're going to do is we're just going to pop these numbers in the right spots. So for a sub 1, we're going to put in an 11, and for d, we're going to put in a 9. And there we have our explicit rule. And we're done with number 5. Number 6, we're going to plug in 85 in for a sub 1. Now, we're going to plug in negative 8 for our common difference. And you can put plus negative 8, or you can write minus 8. I put minus 8. But that's it. That's our explicit rule. All right, so number 7, we're going to plug in a 15 for a sub 1 and a 5 for the common difference. And we're done. For number 8, we're going to plug in a 3 for the a sub 1 and a negative 11 for the common difference. And then for number 9, we're going to plug in a 0 for a sub 1 and a 3.5 for our common difference. Now, because there's a 0 already there, we could just write this as a sub n equals 3.5 times n minus 1. All right, so you can simplify these rules, and sometimes you will need to. So there are 2 steps. First, you're going to distribute the common difference, and then you're going to combine like terms. So for number 10, I'm going to distribute this 6 into the parentheses, and then I'm going to combine like terms. Do not add the 31 and the 6. That's not going to work. Distribute first, and then combine like terms. So for number 10, I'm going to distribute the 6, and then I can combine 31 minus 6, so I end up with 6n plus 25, and that is the simplified arithmetic rule. All right, number 11, let's distribute that 1/2. So I've got negative 2 plus 1/2 n minus 1/2, and then I can combine negative 2 and negative 1/2 and get 1/2 n minus 2.5, or 2.5, or 5/2. I'm not going to be really picky about those because you should know by now that all of those are the same thing. Now, let's look at how to use this sequence. What we have for these problems is we have an explicit rule already written for us, and they want us to find specific values. So the 13th term, the 20th term, down here, we have it written with the other notation. This is the 42nd term and the 100th term. And the key to this is, if they give you a specific number, you're just going to plug that number in for n, and you're going to simplify. So for number 14, we want the 13th term, so we're going to plug in 13. Now, I'm going to put 13 down here for n so that I have a symbol to tell me that, hey, I'm looking for the 13th term. We plugged in 13 for n, do a little bit of subtraction. 13 minus 1 is 12. And then at this point, you multiply the 12 times the 6 and then add the negative 7. You could stick it in a calculator as well, but the 13th term is 65. So anytime they want you to use the explicit rule to find a specific term, you are just plugging that value in for n, and of course you're following the order of operations. So number 15, the 20th term, we're going to plug in 20. 20 minus 1 is 19. 19 times 6 plus a negative 7 is 107. So the 20th term is 107. For 16, we're plugging in 42 for n. So we'd do 42 minus 1 is 41. 41 times 6 plus a negative 7 is 239. And I just typed these into my own calculator. So you are more than welcome to plug them into the calculator and get an answer. Just if you don't have like one of the graphing calculators where you can type everything in all at once, you'll need to make sure you follow the order of operations. All right, last one, we're going to plug in 100. 100 minus 1 is 99. 99 times 6 plus a negative 7 is 587. So the 100th term is 587. All right, let's look at pulling it all together. So we're going to be given a sequence. We're going to write the rule. I'm also going to have the simplified rule there for you when we go through these answers. And then I'm going to show you a sub 15, a sub 50, and a sub 100. So this is a really good one to pause the video on and try to do some by yourself, and then go back through and hear a little bit of the reason why things are going that way. So if you want to pause the video now and see if you can fill out this table, that'd be awesome. All right, number 18, what we're going to do first is we're going to identify the a sub 1 and the common difference. So our a sub 1 is going to be 1,000, and our common difference, we're subtracting 250 each time. So I'm going to plug them in for a sub 1 and for the common difference to create the rule. So a sub n equals 1,000 minus 250, parentheses, n minus 1. And then if I distribute that negative 250, I would end up with negative 250n plus 1250. I'm going to plug in 15. It doesn't matter which one that you use, if you use the explicit rule or the simplified explicit rule, but we're going to plug 15 in for n and get negative 2,500. If you plug in 50 for n, you get negative 11,250. And if you plug in 100 for n, you get negative 23,750. All right, number 19. Our a sub 1 is 13. Our common difference is 11 because we're adding 11 each time, or you could do 24 minus 13. That's 11. I'm going to plug in a sub 1 and the common difference into my equation. So I'm going to get a sub n equals 13 plus 11, parentheses, n minus 1. Or if I distribute that 11 and combine like terms, I'll end up with a sub n equals 11n plus 2. All right, we're going to plug in 15. Doesn't matter if you plug it in for n here or n here, but what we're going to do is plug in 15 and work that out, and you should get 167. If I plug in 50 in for n, I should get 552. And if I plug in 100 for n, I should get 1,102. All right, number 20. Negative 2, negative 5, negative 8, negative 11. So my first number is negative 2. My common difference, I'm subtracting 3 each time. So common difference of negative 3. My formulas are a sub n equals negative 2 minus 3, parentheses, n minus 1. Or if I distribute that negative 3 and combine like terms, I end up with a sub n equals negative 3n plus 1. Plugging in 15, I get negative 44. Plugging in 50, I get negative 149. And plugging in 100 for n, I get negative 299. All right, last one. I've got 0.1, 0.3, 0.5, 0.7. My a sub 1, my first term is 0.1. I'm adding 0.2 each time. So my rule is going to be a sub n equals 0.1 plus 0.2 times n minus 1. Or if I distribute that 0.2 into the parentheses, I get 0.2n minus 0.1. If I plug in 15 for n, I get 2.9. If I plug in 50 for n, I get 9.9. And if I plug in 100 for n, I get 19.9. So there's a lot of stuff going on here, but the main thing is, can we write an explicit rule, and then can we use that rule to predict on way down the road what those numbers are in the sequence? And that's the strength of an explicit rule, is that, if I wanted the 1,000,000th term, all I had to do is plug in 1,000,000 and work that little math problem out and simplify it down to a number. A recursive rule, or a recursive equation, is a rule that gives the beginning term of a sequence and how a sub n is related to one or more preceding terms. You build sequences or patterns like this all the time. Now, a lot of times people have difficulty with this, and it's all about the notation. So I'm going to kind of go slow with you on the notation. You may be able to pick up the pattern pretty quickly, but just keep in mind that the notation is usually where people have trouble with things. So far, we focused on sequences generated by an explicit rule, where the value of each term relates directly to the position of that term. I want the 1,000th term, I plug in 1,000, and I get the answer back. Okay, so that is a very direct thing to do. If I want the second term, and I know what the first term is, I might not want to write an equation for that. So explicit rules, their pros, like the thing that they're the best at is, helping you find numbers very far away. With the recursive rule, you can create the next term by doing something to the term before. So if you don't have to go too far out, oh, I already know the first, second, and third terms, I just need the fifth one, you might want to just continue that pattern. And continuing the pattern is the recursive part of the problem. Okay, so recursive, if you're writing a recursive rule, it has two parts. So it has two equations. The first term is the first part of the equation. So if you know the first term, you write a sub 1 equals, and whatever the first term is, in this case 5, and you're done with that part. The second part shows how to find each term based on the term before it. And here's the notation right here. Let me get my little pointer. This piece right here is what makes everybody want to cry. I don't know why. It just happens that way. So we're going to focus on making sure we are not afraid of this piece. So a sub n we're already used to. We've seen a sub n. It's like y equals. We can plug in a number there. It represents a certain position. Okay. This is a sub n minus 1. And so what we're going to do, let's say we wanted to find the 15th term. We would plug in 15 here. We would also plug in 15 here and think about 15 minus 1. Well, 15 minus 1 is 14. So if I want the 15th term, I need to go back to the 14th term and then add 2 to it. So the sequence builds on itself. So this piece right here is the piece that you need to make sure that you understand what's going on with it. Okay, and so you're going to be using this notation. I need you to make sure that you're not afraid of this piece, because that's usually what happens. People look at it and go, I don't know what to do with this. I'm going to show you. Okay, I'm going to make sure I'm showing you the notation. If you can pick up on the pattern, fine, but go ahead and realize that when you get to the ACT, they're going to do things like this and use this notation because the notation scares people. And so if you don't know how to use this, then, you're not going to know how to work the problem. The problems aren't too bad, though. So let's look at some examples. Actually, let's look at how to write the recursive rule. So you have to have two equations. The first one is going to be a sub 1 equals a number. That's it. The second one is going to be a sub n equals a sub n minus 1. Now, these pieces don't change. The only thing that's going to change is this plus the common difference. So this piece is going to be replaced with plus or minus a number. You're going to have a sub n. You're going to have this equals a sub n minus 1. That stuff's not going to change. You're going to have plus and then or minus a number. So we're going to start by finding the first 5 terms in the sequence. So they give us the first number. Then they also give us a sub n equals a sub n minus 1 plus 3. And that's our common difference. So we're adding 3 each time. Now, they want the first 5 terms. Well, we already know the first term because they gave it to us here. The first number is 5. How do I know that's 5? Because that's 5. They have to give you a piece to start with. If they don't give you a piece to start with, you can't build a sequence. If I said, hey, I want you to build a sequence, add 3 each time, you're going to be like, where do I start? So if I don't give you a starting point, you can't build a sequence. So we have to be given this first term. So here's our first term. Our first term is 5. Now, to get to the next term, you notice here there's a 2, right? A sub 2. We're going to pretend like we put a 2 in for this n. But you also have to put a 2 in for this n. So that means we've got a sub 2 minus 1. And looks like my line kind of hit it, but there's a minus in between that 2 and that 1. So a sub 2 minus 1 plus 3. Well, let's simplify that. 2 minus 1 is 1. So a sub 1 plus 3. And don't we know a sub 1? A sub 1's up here. A sub 1 is 5. So this is really 5 plus 3. And 5 plus 3 is 8. Now that 5 is the same as that 5, and that's the same as that 5. So we're going to use the numbers in the sequence that we're building to create the next numbers. All right, let's look at a sub 3. So what we're going to do, we've got a 3 here. We're going to pretend that we put a 3 in for this n. We're also going to put a 3 in right there and make that a sub 3 minus 1. Sorry about that again. Looks like my minus sign's hidden by the bar. Okay, so a sub 3 minus 1, and then we still got that plus 3. And we're going to simplify. 3 minus 1 is 2, so this is really a sub 2 plus 3. And a sub 2, that's this number up here. A sub 2 equals 8. So we're going to plug that in. That's going to be 8 plus 3, and 8 plus 3 is 11. Now, some people may be going, hey, we've got 8 here and 8 here. Is that the same 8? Yeah, it's the same 8. So to get this number, I had to look back at the number before it and add 3 to it. To get this number, I had to look back at the number before it and add 3 to it. So that n minus a sub n minus 1 means is go back a number and add 3 to it. All right, let's keep working with our notation. So I've got a sub 4. I'm going to put a 4 here, but I'm also going to put a 4 here. So that's going to be a sub 4 minus 1 plus 3. And 4 minus 1 is 3. A sub 3 plus 3. Well, a sub 3 was this number over here. A sub 3 is 11. So that's going to be 11 plus 3, which is 14. And yes, those 11s are the same 11. A sub 5 is going to be equal to a sub 5 minus 1 plus 3. A sub 5 minus 1 is a sub 4 plus 3, and a sub 4 is up here. That's at 14. 14 plus 3 is 17. And really what I've done is I've created a sequence. 5, 8, 11, 14, 17, where I started with 5, and I'm adding 3 each time. But it's not spelled out that way. I have to understand what this is telling me. Okay, so this is how the notation is being used. Especially if you need that or you want to understand that better, you can use it. But if you're like, oh, this is just telling me start with 5 and add 3 each time. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. 14 plus 3 is 17. That's a different way to do it, and it's perfectly valid as well. All right, so let's look at example 2. Example 2, we start with a sub 1 equals 2. So we're starting with 2. And this says I'm going to find a number, I'm going to take the number before it and subtract 1. So my first number is 2. To get the next number, I'm going to take 2 and I'm going to subtract 1 off of that. 2 minus 1 is 1. To get the next number, I'm going to take the number before, which was 1, and I'm going to subtract 1 off of it. 1 minus 1 is 0. To get the next number, I'm going to take the number before, which is 0, and I'm going to subtract 1. 0 minus 1 is negative 1. To get the next number, I'm going to take negative 1, and I'm going to subtract 1. Negative 1 minus minus 1, is negative 2. Now, do you see a lot of repeating numbers? I do. I'm taking the answers and using them in the next line. So the answer here gets used in the next line to create the next number. The answer here gets used in the next line to create the next number. Okay? So they have to tell you where to start. They have to tell you what you're doing. In this case, we're subtracting 1 each time. And you keep doing that. So, I mean, the sequence 2, 1, 0, negative 1, negative 2 isn't too bad of a sequence. It's the notation that gets people. So just keep that in mind. Now, number 3 is a very interesting sequence. So we're going to start with 31, and then here's our rule, we're going to take 20 and then we're going to subtract off the number before. Okay, so we're going to start with 31. To get this number, a sub 2, I'm going to do 20 minus 31. So 20 minus 31 is negative 11. All right, to get this number, I'm going to do 20 minus negative 11. So 20 minus negative 11 is 31, which that's the number we started with. All right, to get this number, a sub 4, I'm going to do 20 minus the number before. 20 minus 31, negative 11. All right, to get the next number, I'm going to do 20 minus the number before, negative 11, and I'm going to get 31. So it's an interesting sequence that kind of goes back and forth between those two numbers. Okay. Now, I was going to say something, and I forgot. It'll come back to me. But anyway, so that is how to use those. And again, if you need to use the notation, plug in, for the 6th term, plug in a 6 there and plug in a 6 there. It'll tell you what number to use, but it's usually you're going just back a number to continue on. All right, let's write a recursive rule to model the sequence. So I've got a table, 1, 2, 3, 4, 5, 2,000, 2,500, 3,000, 3,500, 4,000. And so remember that in order to write this, I need 2 equations. And that's a big deal because a lot of times people forget that there needs to be 2 parts. A lot of times they'll focus on the second part and they'll forget about the a sub 1. You have to start or tell where the sequence starts. So what is our first number? It looks like our first number is 2,000. So a sub 1 equals 2,000. What are we doing each time? Looks like I'm adding 500. So I'm going to put in a 500 for that common difference. And there I go. That is my recursive rule. Now, if I wanted you to find the next number in the sequence, would you be able to do it? Because it's recursive, right? All you're doing is you're adding 500 each time. So, you would just say, well, the 6th term's 4,500. The 7th term is 5,000, right? But if I asked you the 1,000,000th term, you'd be like, this isn't good enough. I want the explicit rule, okay? So this is helpful for how to find things close by, right? Not how to find things, numbers that are far away. All right, so let's look at example 6. Remember, we need the first term and we need the common difference. So a sub 1, what's our first term? Looks like 5,000. So a sub 1 equals 5,000. And then my common difference, I'm adding 1,000 each time. So a sub n equals a sub n minus 1 plus 1,000. So to figure out the 6th term, I look backwards at the 5th term. That's at a sub n minus 1. And I add 1,000 to that number to get the next term. So that would be 10,000 in this case. All right, write a recursive rule to model the sequence and then find the 6th term. So here I have a set up. So we just need to fill in the first term. Looks like our first term in example 7 is 74. And we need to figure out what our common difference is. Looks like we're subtracting. It looks like we're subtracting 7. So a sub n equals a sub n minus 1 minus 7. All right, now I already have the first 4 terms. So I just need to figure out what the 5th term is and then the 6th term, and then I'll be done. So I know that I'm subtracting 7 each time. So to find the 5th term, I'll take a sub 4, 53, and subtract 7. So the 5th term is 46. And to get the 6th term, I'm going to subtract 7 again. So I get a sub 6 is 39, and 39 is the 6th term. So I'm just extending that pattern. So sometimes, like we're going to find here in a little bit, the 11th term, it might be a little tedious. Tedious just means I have to keep doing the same thing over and over again. It's not going to necessarily be hard. It's just going to be like, are we done yet? Kind of thing. And so to go and find the 1,000th term or the 1,000,000th term is going to be super tedious. That's where the explicit rule kind of takes over. And it's like, oh, all you got to do is pop in 1,000,000 and then you get the number back out. All right, so let's write the rule. So a sub 1 equals, looks like our first number is 25. Looks like we are adding for each time. So the second part is a sub n equals a sub n minus 1 plus 4. And so what we're going to do is we're going to go ahead and label. We've got the first 4 terms. The fifth term will add 4 to 37 and get 41. Add 4 again to get the sixth term. Add 4 again for the seventh. Add 4 again. Add 4 again. Add 4 again. All right, we get the 11th term, 65. Okay, so it's a little tedious. We're adding 4 each time, but really adding 4 isn't too bad. Now, some people will be like, well, I'm adding 4, 1, 2, 3, 4, 5, 6, 7 times. Can I just add 28 to that? Sure, you can do that. But it's, you basically, when you do this, you're either coming up with, because basically when you do that, you're looking at using the explicit rule. But you're basically building the sequence when you find the 11th term or the 6th term. You're building that sequence out is really what you're supposed to be doing with the recursive model. All right, so explain in your own words how you would find the 100th term in any recursive sequence. Here's what I would do. I'd start with the first term, then find the second, then the third, then the fourth, then the fifth, and so on and so on and so on until the 99th term, and then I add or subtract one more time, and then I'll find the 100th term. And that sounds like a pain in the butt. I wouldn't want to do that for a recursive sequence. So if I had to choose between recursive and explicit, and I had to find the 100th term, I'd choose explicit every single time. Unless I had nothing else better to do, or I just felt like adding 12 every time, whatever it is I'm doing.